Welcome to Inverse Functions Part 3. This will be our last video on inverse functions. Specifically, what we're going to learn today is how to use function composition to show that f in its given inverse is correct. And then we are going to talk about domain and range of a function and its inverse. Okay. So properties of inverse functions. So the composition of f and its inverse is equal to x. And you'll see that written as f composition with f inverse is equal to x. And the other way around, the composition of the inverse in the function is equal to x. So f inverse of f of x is equal to x. Okay, so this property can help us to show that f in its given inverse is truly its inverse. And note that you must check both. So you must do f of f inverse and f inverse of f and show that both of those are equal to x. Okay, so example 1, for the function f, use function composition to show that the inverse is as given. So first, we will do f of f inverse of x. Okay, so that means that f, or 5 over 4 x is going to go into the x in f. So we have 4 over 5 times 5 over 4x. And so you can work with fractions differently. You might see that the 4's cancel and the 5's cancel. But if we were to multiply, this would be 4 times 5 over 5 times 4 and then times x. So this is the variable x. Okay. This gives us 20x over 20, which reduces down to just x. So that one checks off. And remember, we need to check both. So now we need to do f inverse of x. Okay, so we're going to do f inverse of f of x. Okay, so f inverse 5 over 4, and we are going to input in 4 over 5x. Okay. And so in this case, I'll cancel the 5's cancel, the 4's cancel, and I'm just left with 1x, which is just x. So you've shown both, which means that the function and its inverse is as given. Okay. Number 2, for the function f, use function composition to show that the inverse is as given. So we have f of x is equal to x plus 7 over 3x minus 4, and f inverse of x is equal to 7 plus 4x over 3x minus 1. So we're going to start off with the composition of f inverse. Okay, so this function is going in for each x in f. Okay, so what that looks like is we have 7 plus 4x over 3x minus 1. Then we have plus 7 over 3 times, we have x, so instead of x, we're inputting in f inverse. And then we have minus 4. Okay, so we have a lot of fractions going on here. I'm going to rewrite this on the next slide, but one thing that I am going to point out is this 3 times. This term in parentheses, you can keep the 3 with the denominator. In fact, that's where it goes. So this is 3 times 7 plus 4x. So that's what you'll see me write on the next slide. Okay, so we have 7 plus 4x over 3x minus 1 plus 7 over 3 times 7 plus 4x over 3x minus 1 minus 4. So what in the world do we do with all of these denominators, right? Well, notice that our least common denominator out of all of them is 3x minus 1. So what we can do is we can take every single piece of this and multiply by 3x minus 1. So here's what that looks like. I'm going to multiply this piece by 3x minus 1, this piece by 3x minus 1. Okay. Okay, so what happens is we get a lot of cancellations and we no longer have fractions within fractions. Okay, so when we have 7 plus 4x over 3x minus 1 times 3x minus 1, the 3x minus 1's cancel out. And then the numerator, we have 7 plus 4x plus 7 times 3x minus 1. Not so bad now. Okay, same thing in the denominator. The 3x minus 1's cancel, so I'm left with 3 times 7 plus 4x minus 4 times 3x minus 1. Okay, so now what we'll do is we'll distribute everything. So in the top we have 7 plus 4x, and the 7 times 3x is 21x. 7 times negative 7 is minus 7. Divided by 3 times 7 is 21. 3 times 4x is 12x. negative 4 times 3x is negative 12x, and negative 4 times negative 1 is positive 4. So now we simplify numerator and denominator. So we have in the top, our 7's cancel, and we're left with 25x. In the denominator, our 12x's cancel, and we have 25. 25x over 25 is just x. Okay, so for this problem, I'm going to leave it to you to do the second part, which is f inverse of f of x. And as you're doing it, if you have any questions, concerns, let me know. It works very similarly to what we just did. But for the sake of time, I want to make sure that we are able to talk about domain and range and graphing. Okay, so domain and range of inverse functions. So the domain of f is the range of its inverse, and the domain of the inverse of f is the range of f. So the way that I like to think about this is we talk about how to find domains. So if you can find the domain of f, that means that you can find the range of f inverse, and finding the domain of f inverse gives us the range of f. Okay, so the domain here is the range here. This is just a visual. The domain of f inverse is the range of f. Okay, so we are going to do an example of that. So also what we're going to also do is find the inverse of a function. So remember that if a function is 1-to-1, it has a unique inverse. To find the inverse, we replace f of x with y, we interchange x and y, we solve for y, and then we replace y with our inverse notation. Okay, so 1a, find the inverse of the given 1-to-1 function. So this is already telling us that our function is 1-to-1. Now it's our job to find the inverse. So the first step is to replace f of x with y. The second step is to interchange x and y. And the third step is to solve for y. So in order to do that, we need to get rid of our denominators. In this case, I'll show you cross multiplication. So if we put this over 1, we have x times y minus 6 equals 1 times y plus 5. Okay, and then we're going to keep solving. So I am going to distribute everything. So x times y is xy. X times negative 6 is negative 6x. And then 1 times y plus 5 is y plus 5. Okay, now recall that our goal is to solve for y. So we want to get our y's together on one side and everything else on the other side. So what I'm first going to do is subtract y from both sides. Okay, now I don't have like terms, so this is xy minus 6x minus y is equal to 5. Okay, even though this has a y in it, it's xy, which is different than just y. Okay, now I'm going to add 6x to both sides to get my y's together. We have xy minus y is equal to 5 plus 6x. And now in order to solve for y, I can, on the left-hand side, I can factor out a y from both terms. So both of these have a y, so if I divide a y out of both, I'm left with x minus 1 is equal to 5 plus 6x. Okay, so we're still on step 3. I'm going to rewrite this and go to the other slide. So I have y times x minus 1 is equal to 5 plus 6x. Okay, now to solve for y, all we need to do is divide by x minus 1. Okay, so we have y is equal to 5 plus 6x over x minus 1. And my last step is to use inverse notation. So instead of y, I have f inverse of x is equal to 5 plus 6x over x minus 1. Okay. Phew, a lot of fractions there. Next, give the domain and range of f and its inverse function. Write your answer in interval notation. So first, what I suggest doing for a problem like this is to find the domain of each. So f of x, let me move it over. F of x was equal to x plus 5 over x minus 6, and f inverse of x, which is what we just found, is equal to 5 plus 6x over x minus 1. Now remember, when we have denominators, our restrictions are our values that it cannot be are values that make the denominator 0. So in the case of f of x equals 6 makes the denominator 0. So picture this number line as all of our possible x values, and it can be anything besides that. So in interval notation, we have negative infinity to 6, union 6 to infinity. So that's my domain of f. Okay, my domain of f inverse, x cannot be 1. Okay, so again, if I and visualizing all possible x values, I can have anything but 1. So my domain is negative infinity to 1, union 1 to infinity. So let's put this together to answer the question about domain and range. So the domain of f, I guess I should have made this bigger, was negative infinity to 6, 6 to infinity. And by the property of domain and range in inverse functions, this is also the range of f inverse. Okay. The domain of f inverse was negative infinity to 1, union 1 to infinity. This is the range of f. Okay. So it's pretty cool. We've usually only talked about range looking at a graph, but now using a function and its inverse, we can get the domain and range of all of those parts. Next, part of this question is to graph f and its inverse on the same plane. And so we haven't really talked about graphing a function like this, so we're going to talk about how to do that and how to sketch it. Remember that you can graph f and then reflect it across the line y equals x in order to graph the inverse. Okay, so first I'm going to show you what it looks like on a graphing software called Desmos. So I am going to graph f. I should have it right in front of me, which is y equals x plus 5 divided by x minus 6. Okay. So here is what the graph looks like. Now, how do we know that it looks like this using the tools we're given in this class? So when you see something like this, where we've got, a linear over another linear function and they're being divided, it's going to look something like this, or even, oh, that's going to have me pinch zoom. So let me go back. So our options are really like this or like this. Okay, so you can plot points to see where it's going to end up. For something like that, also if you're matching to graphs, you can plot points and make sure the ones that you're matching look something like this. Okay. So there's a couple other ways that we can graph this. The first is, remember that for f of x, we had x plus 5 over x minus 6. And we also determined that x is not allowed to be 6. So that means it's what's called a vertical asymptote, that the graph is never going to cross this line. Okay. The other thing that we can do is notice, and this is what's called our horizontal asymptote, is we can look at just our leading term in the top and bottom. This is x over x, which gives us 1. Okay, so that means that along the line y equals 1, we have a horizontal asymptote, which means it's never going to go below or above that. So for this graph, it would look something like this. Okay. You don't have to know horizontal and vertical asymptotes. I wanted to show you what it looked like on Desmos. And then you can also plot points as well. I would pick values that are somewhat convenient so you don't have a lot of fractions going on. And as I mentioned, a function like this is 1-to-1. So if you have to graph it to determine it's 1-to-1, you can sketch something like this as well. Thank you for watching. If you have any questions, feel free to reach out to me.